Well, hello. Today I'm going to tell you about Maxwell's four equations and how they govern the world. Well, it's really not a joke because I know you love your mobile phones and your internet. Also, you are only able to watch the cat videos and eat midnight microwave snacks all because of Maxwell. Well, first I'm going to tell you about the two basic equations of Maxwell, which are the first two equations, that is the Gauss's law for an electric field and the Gauss's law for a magnetic field, which pretty much are the basic need to know for electromagnetism. Well, let's start with the Maxwell's first equation, the Gauss's law for an electric field. This right here is the equation, and this right here is the arbitrary shape or surface which has a net enclosed charge in it. Now, the Gauss's law of an electric field provides us with a relationship between an electric charge and an electric field. Now, for those of you who do not know what an electric field is, well, it's just like a gravitational field. Like a gravitational field, when an object is thrown up, it comes down. Why? Because it experiences a force of attraction, because gravitational field surrounds us all. Similarly, there is electric field surrounding us all, where two charges, when placed in it, are acted upon by forces which cause them to repel and attract to each other. Let's see. Here, I've got two charges. Well, they're light charges. Let's bring them closer. They repel. Why? Which is, the very basic law of electrostats. Light charges repel. But why do they repel? Because they're acted upon by forces which are caused by the electric field surrounding them. Right here in space. Yeah. See? This is what an electric field looks like. So now with the equation. Here, the left side of the equation is electric flux, which is nothing but the electric field lines passing through a closed surface. Just like this. This is electric flux. And the right side of the equation is the net enclosed charge divided by the permittivity of free space. This net enclosed charge is the closed charge within the surface through which electric field lines pass through. So this is the first equation of Maxwell. Gauss's law for magnetic fields is similar in form but different in content from Gauss's law for an electric field. The Gauss's law for magnetic field states that the total magnetic flux passing through any closed surface is zero. In other words, if you have a real or imaginary closed surface of any size or shape, the total magnetic flux through the surface must be zero. Well, on to the third equation, that is the Maxwell-Faraday equation. Faraday demonstrated that the electric current may be induced in a circuit by changing the magnetic flux enclosed by the circuit. This discovery was made even more useful when extended by Maxwell to the general statement that a changing magnetic field produces an electric field. Well, let's look at our third equation, that is the Maxwell's third equation, also known as the Maxwell-Faraday equation. All you need to know about it is the electric field, which I told you what it is, and the magnetic flux, which is pretty much similar to the electric flux, which is the number of magnetic field lines passing through a closed surface. So now, what does the equation do? What is it about? It is that if the magnetic flux through a surface changes, an electric field is induced along the boundary of that surface. So if a conducting material is present along the boundary, the induced electric field provides an EMF that drives a current through the material. Thus, quickly poking a bar magnet through a loop of wire generates an electric field within that wire, but holding the magnet in a fixed position with respect to the loop induces no field at all. Well, isn't it interesting? This is the changing magnetic flux and this is the electric field. So, the most common examples of this equation are very basic things that govern electricity in our homes and places, which are generators and transformers. But I think the best example would be an electric generator. So let's see how an electric generator works. This is an example of a generator that powers a light bulb. It contains, as you can see, stationary magnets of opposite poles, an armature, a commutator, and a shaft, which are all attached to a circuit working to produce electricity. The shaft rotates by mechanical energy supplied, which makes the armature to rotate and magnetic flux to vary as the area varies, thus inducing a current in the circuit and lighting up a bulb. Well, interesting, right? What's more interesting is this.
Yes, aurora. Beautiful, aren't they? Well, they're caused by a geomagnetic storm, which is caused by a solar wind shock wave. So, a surge in the flux of charged particles temporarily alters the Earth's magnetic field, which induces an electric field in the Earth's atmosphere, as shown by the Maxwell's third equation. And the auroras you see are the result of ionization and excitation of atmospheric constituents that emit lights of varying color and complexity. Okay, let's get to the fourth equation of Maxwell. It says that an electric current or changing electric flux through a surface produces a circulating magnetic field around any path that bounds that surface. Also, Maxwell combined displacement current with some of the other equations of electromagnetism, and he obtained a wave equation with a speed equal to the speed of light.
So, this right here is the fourth equation of Maxwell, the Ampere-Maxwell law. The left side of this equation is a mathematical description of the circulation of the magnetic field around a closed path, let's say A. The right side of the equation includes two sources for the magnetic field, a steady conduction current and a changing electric flux through any surface, let's say B, which is bounded by path A.
He said that light and magnetism are affections of the same substance, and light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Thus, EM waves were born. Now, I cannot emphasize how crucial this contribution of Maxwell was. Like everything from internet to radio to your mobile phones, Wi-Fi, everything works on the basic principles of EM waves.
Radio waves transmit music, messages, and data through the air over often millions of miles. Whether we are talking about a cell phone, sensors, headphones, or any one of the thousands of wireless technologies, all of them use radio waves to communicate. GPS satellites continuously orbit the Earth. Space vehicles transmit microwave carrier signals, which are a type of electromagnetic radiation. The users of GPS have receivers that convert these satellite signals so that one can estimate the actual position. Even things like the radar and microwave ovens depend on radio waves. Things like communication, navigation, and even modern aviation would be impossible without radio waves. As we saw, Maxwell's equations do govern the world. I think he believed that the science of his day would be the technology of this day. And I believe there are still great things waiting to be discovered and invented, because exploration is in our nature.